Hi, Julie. How are you?
Hi, Alex. I'm good. Yeah, let's wait the uh attendance coming. Yeah.
Okay, sure. No worries. Julie, can I test to see if you can see my presentation when I share the screen?
Yeah.
Okay, thank you.
You're going to text. Yeah.
Okay, are you able to view it?
Yeah, it works.
Okay, got it. All right, thank you.
Hi, Alex. I think we can wait for 3 minutes. Yeah, and because
Okay,
people are
sure.
yeah.
Yep, sounds good.
Hi, Alex, everyone. I think we can start. And let me, sorry, let me share my screen.
Okay, sounds great. Yeah, hi, everyone.
Yeah, and I can give a brief introduction about our workshop today. Yeah, and hi, everyone. Welcome to our October 2024 Virtual Learn and Earn workshops hosted by Build Her. And I'm Julie, in charge of the programming. And I'm thrilled to have you all join us today from various corners of the world. Sorry, I think there's no, oh, okay, sorry. And also, as you see, here's our team of Build Her, and Rox and Annie is our co-founder, and Zara is in charge of the social media. And in this slide, you can see these all of my from our partners of these workshops, and we are also grateful to our partners whose support has been vital in making our workshops possible. And you can see it's Henry, ZKM, and Matthias, and also the Elio. And also in this slide, you can see all of the picture is from our live events. And also here is our resources. And you can, here is our resources. It's included our developer docs and submission forms. And after you complete all of the tasks, and please feel free to submit all of the forms in case you can get the rewards. So let's all. So Alex, please let's get started about your presentation.
Yeah, sounds great. Thank you so much, Julie, for the intro, and hi, everyone. Really nice to meet you guys. I'm wondering, Julie, would you be able to stop sharing your screen? All right, thank you.
Sorry.
Yeah, it should be all set, no worries. Yeah, hi, everyone. Wondering where you guys are from in the world. Do you want to put in the chat where you guys are from? So I'm from Boston, but I'm currently like outside of LA in California. That's where I'm from, but curious to hear where you guys are from in the world. While I'm getting this set up. Nigeria, oh cool, nice. Istanbul, Pluto. Nepal, cool. So we have everyone from worldwide. It's really great to see so many like audience members from different parts of the world. And thank you so much, especially if this time is either really early in the morning for you or really late. Thank you so much for joining from Nigeria. Nice. All right, we can get started now. So hi, everyone. I'm Alice. I'm education lead at ZKM. Today, we're going to go over how you can generate zkMIPS proofs with ZKM. So we'll be going over why zkVMs, what's their use case, an overview of zkMIPS, which is specifically ZKM's zkVM, and also a demo of just generating and verifying a proof. All right, so what exactly is ZKM? Well, ZKM is building a general purpose zkVM, also known as zkMIPS, based for verifiable computation based on the MIPS architecture. But why exactly are we building a zkVM? Why are zkVMs needed? Well, today, if I want to ensure that any type of computation was correctly done, we would have to verify the accuracy and also the integrity of the result of the computation. Right now, there's two different ways of doing this. So first, you could do it through an outsourced trust model, so have someone else do that computation for you, or you could verify it by yourself, a self-verification model. So that first model really relies on trusting some sort of external entity or some sort of third party to perform that computation correctly and to provide that correct result for you. So you're putting trust into someone else. And that could be, for example, like a cloud service provider. Typically, it could be some sort of centralized server or database like AWS. So you would have to trust that they're doing that computation correctly and not tampering it or not trying to like cheat you, for example. So there's a huge trust assumption that's involved in this first model, the outsourced trust model. The other option, if you're not really comfortable with the first, is doing that computation yourself. So you would have to rerun the computation on your own end. And that gets rid of the trust assumption, but it's pretty costly and it's also inefficient because it's repetitive, it's duplicative, and if you want to run a computation that's already been run, well, you're doing double the amount of work. So as you can see, each of our models here, they have some trade-offs in terms of costs, in terms of security, trust assumptions, scalability. So while the first model relies on trust and it may lack in security and transparency, it's more scalable and it's cheaper than re-executing the computation. But by re-executing the computation, it has that advantage of not having any sort of trust assumptions that are involved with a third party. But what if there was a way to get the best of both worlds? Can we make it cheap and scalable for a third party to verify a computation without having to rely on trust? So we may find a solution to this through verifiable computation with proofs of knowledge. It's a two-party protocol that involves a prover and verifier. A prover can be a single user or client like yourself. Then they would basically outsource that computation to the verifier, and that verifier is commonly computationally more powerful, like for example, some servers in the cloud. So if we're using the example of you could be outsourcing a computation to a server, and then it's able to verify the correctness of that result. So the prover will perform a computation, and then they will produce the result of that execution. And then from there, they will also produce a proof that that computation was executed correctly. From there, the prover will first send that proof to the verifier, and then the verifier will check that the proof was indeed executed correctly. So in that way, we have untrusted parties like the prover and verifier. They don't even need to know each other personally. And we can have untrusted parties that can perform this computation without having to have those trust assumptions. So when we're applying proofs of knowledge to blockchain applications, there's a few different properties that we should consider for our proofs. So first, they should be non-interactive between the prover and verifier. This makes it so that the parties involved can be untrusted, and it also allows for a larger number of people to verify the proofs, not just one person. And we also should make our proofs succinct. That means our proofs are short and also very easy to verify. So the verifier's work is easy. And another property is ZK, or zero knowledge. This is optional. This is just in the case if the prover wants to keep the solution a secret. And with the ZK proof, it makes it so that it does not reveal any sort of additional information about the solution. So it's really good if you have any private information that you want to be kept just to yourself. Now, the types of computational problems that these proofs of knowledge can apply and extend to, for example, transition functions for layer 2s. We see this a lot in ZK rollups. Essentially here, the layer 1 is the verifier, while the layer 2 is the prover. So the layer 1 could be, for example, Ethereum. It's like a computer in the cloud. It's slow, it's expensive, scalability is an issue. But the idea here is to outsource those computations off-chain from the layer 1 onto the layer 2. And then that layer 2 would send that resulting new state with a proof back to the layer 1. So that's just an example of a proof of knowledge where we're able to scale transactions on Ethereum using ZK rollups. But another example is the execution of smart contracts. That's the main function of zkEVMs. Those are typically written in Solidity, and the EVM will verify the execution of that contract. And then a third example, which is what we at ZKM are focusing on, is the execution of off-chain programs. So not just those within Ethereum or within the Web3 space, but any type of computational problem, any type of program. So what we do is an off-chain program is given, and zkMIPS will verify that the execution of that program is indeed done correctly on-chain. So then the verifier would like to verify the correctness of the execution, and then the prover would provide a proof that that program was correctly executed. So we can prove the execution of any type of program that you would like. If we take a closer look at the stages of the life cycle for these proofs, it first starts with an end user's action. So the end user wants to prove the correct execution of a computation. This is the business logic that part for these applications that are using ZK proofs. So the questions that they're answering is, what exactly do I want to prove? So some examples include maybe some smart contract function calls, or you want to prove that a token transfer on a rollup was executed correctly, or maybe some other blockchain-based transactions. And then from here, our next step in this life cycle is the program execution. So from there, our next question is, we need to determine how will this be executed. If the computation is in the form of a program, that program will be executed in an environment that's able to compile to a readable format. So for example, if you're writing a ZK circuit, it would be an algebraic circuit or machine code. So for ZKM, that program is compiled to MIPS. And then our next step is, how will our proof be generated? So that we can have a proof for that program's correct execution. There's a few different ways of doing this. You could generate your proof locally, or you could outsource it and use a proving service and utilize proving markets that are out there. The means of how you generate your proof doesn't really matter. It's just up to your preference. From there, as our next step, now that we have our proof generated, now we need to figure out how can we verify it. So this can be done off-chain, or if it's on-chain, a very common way is to use verification layers, or just directly on Ethereum by posting that proof on a smart contract. And then now that you have your proof generated and also verified, now the next step is the resulting action. So with the proof, resulting action can occur depending on the application. So for example, if we're trying to prove a blockchain-based transaction, the resulting action would be that it's settled. So from there, the cycle repeats, and that's just a bit of an overview of the proof life cycle. Now the vision here is, what if a proof of execution can be provided for any type of computation? So both blockchain-based and non-blockchain-based. This doesn't have to restrict strictly to our Web3 applications, but even computations beyond, like ones that we use every day in our everyday lives. So that's the main vision that zkVMs are attempting to fulfill, that kind of general computation where a proof can be provided for any type of program, so both blockchain and non-blockchain based. zkVMs, like ZKM, they address each stage in this proof lifecycle that we just talked about, and its main value proposition is providing a developer-friendly experience. So developers can write programs that they want to prove using high-level languages that they're already familiar with. So right now, ZKM currently supports Rust and Golang. The alternative to this, kind of like the status quo, if you want to write ZK proofs, would be having to use domain-specific languages or writing the circuit out directly. So those are both hard, they're difficult, there's a very big learning curve that's attached. But here you don't need to learn any new skills in order to generate a proof. You can just use a program that you've written in a language that you're already familiar with. So that's really the main value proposition behind zkVMs. And also zkVMs, they provide an execution environment. So it's in the form of a VM to execute the program. All zkVMs have a prover component to generate proofs. That prover component varies depending on the type of zkVM, depending on the design choice that the project makes. or some hardware configurations involved, but we'll be going into some more details about zkMIPS's specific prover in a little bit. But in terms of the verification, many zkVMs like ZKM use smart contracts to verify the proofs on chain. And then another value proposition that I want to mention, in addition to being more developer friendly, is its breadth of use cases and applications. So for zkMIPS specifically, we're targeting the MIPS instruction set. This can be applied to both blockchain and non-blockchain settings, as we mentioned before. But for zkVMs more focused on the privacy side, you can have some use cases that are more geared towards private computations that can now be possible on public blockchains. But ZKM's main application, because we're focused on the succinctness aspect as opposed to the privacy part, we're more focused on interoperability. So providing unified native liquidity across independent, incompatible ecosystems like Ethereum, like Solana, like those move-based ecosystems as well. So providing a very interoperable method for interacting with those different chains. Now, continuing our discussion on why we should use a zkVM, I'll speak a little bit about the alternative, which I mentioned very briefly, about writing circuits directly. So in this case, even though circuits are pretty highly optimized and efficient, because the circuit is going to be exactly what's required for the program, and there's no extra components that you have to deal with in a zkVM like memory, it's generally better, like despite this, it's generally better to make circuits that's constructed into an actual VM. If we look at the differences here between the circuit-based approach and between the zkVM-based approach, with a zkVM, instead of a circuit being equivalent to a program, we can have a circuit that knows how to execute a program. And while a circuit is specific to each program and a special verifier needs to be defined every single time, on the other hand, a zkVM can be thought as a generalized universal circuit. So you only need to define the verifier once. It relieves a lot of burdens on the developer side. And then another benefit zkVMs has is the ease of adoption. So any developer can use a zkVM because, again, they can use their preferred high-level languages, and it doesn't really matter what language they use because that language will be compiled down to machine code for the VM to read. Whereas for circuits, only a small subset of people, only very specific developers are able to do this because you need the additional knowledge of writing in these specialized languages, writing circuits, defining constraints, using the cryptography that's in the context of all of this. And there's a pretty steep learning curve that's attached. I think in the world, only a couple thousand people know how to write circuits. So really not that many people compared to the number of developers in the world. So there's a pretty steep learning curve involved, but with zkVMs, you don't really need to learn anything additional before you can start implementing. So for this reason, a lot of zkVMs in the market right now, they really emphasize the benefit of using the time to build applications. Like, what am I going to use my zk proof for, instead of using that time to write circuits. And also, I do want to mention that zkVMs also have the advantage for an easy path to recursion. So for example, after you run your first program, you can take the proof that's generated from that first program and pass it as an input into the zkVM again. Then you can run a verification program, and then you can get another proof that proves that the first proof that you generated was correct. So that recursion aspect is very difficult to complete with circuits, but relatively easier compared to for zkVMs. Now, if we compare zkVMs to zkEVMs, one of the main benefits for zkVMs is that they're built on well-established and also mostly unchanging instruction sets like MIPS and RISC-V. The EVM, on the other hand, they frequently undergo some opcode changes, and that may lead into the actual zk circuit that it's being built on to change as well. In terms of scalability, zkEVMs, they really only support Ethereum Geth, but zkVMs can support a variety of programs written in many different languages, and they also have applications beyond those in the blockchain scenarios. So those are some of the main advantages with zkVMs over our zkEVM approach. And here's just a landscape map that was made by House of ZK, that's ZKM's media and podcast channel. But if we scope out a bit and examine that broader ZK landscape as a whole, we're seeing ZK projects become much more specialized and also a lot more optimized for these stages in that proof lifecycle. The proving services, for example, like we can see here, they are very focused on scalability and reducing costs for the proof generation stage in that lifecycle. And cross-chain projects, this is another category in our landscape. They're focused more on the interoperability component. So some of them are addressing the issue of fragmented liquidity. And there's also in this landscape other layer ones, which include verification layers and also providing toolkits to write ZK dApps. So they're really focused on optimizing for the developer experience. We can also see for like zkEVM solutions, they're more specialized towards Ethereum-based applications. So you can think of it as a very specialized type of zkVM specifically for Ethereum. And these projects on this map right here, they are the main kind of ZK infrastructure projects that will help lay out the ground for wider scale, real world ZK applications to be built on top of. So most of us in this landscape really have this shared vision of making ZK more widely accessible, more widely adopted, so that we're not just limited to our conventional ways of our computations, which involve trust and also re-execution. Now for our second part, we're going to go over some more details about zkMIPS specifically. But to understand what a zkVM is, we first will answer what a VM is. You can think of a VM as a kind of program that can run other programs. EVM, you guys may are familiar with, is a type of VM that can run Ethereum smart contracts. So in a VM, we have a program that's compiled down to VM readable code or machine code. And there's also an input to the program. So both this input and that program are fed into the VM, and then a final state of that program will be outputted. A zkVM adds onto the VM a few extra components. So for a zkVM, you can think of it as a ZK circuit that runs a VM in order to prove that a program was correctly executed. So in addition to having your input and that program that's compiled down to machine code, we also have what's called a witness. The witness are the values that the verifier does not read. So either because they are private to the prover, so they act as secret inputs, or because they may just be too long for that proof to be succinct. Remember, another one of our priorities when it comes to proofs is the succinctness component. So we want our proofs to be shorter so that they cost less and it takes less time to verify. But for, in this case, we have our input, our program, and our witness. Those are all fed into the zkVM. And in addition to our output of the program right here, we also have a proof that proves the correct execution of the program. And this is also generated. And in the bigger picture, if we look at the placement of the zkVM with all the other components that are involved, we can first see that a program will be fed into a compiler. That compiler depends on the type of instruction set that the zkVM is going for. So in our case, that compiler will compile our program down to MIPS. It could vary depending on the type of instruction set used in other projects, but in our case, it compiles down to MIPS. And then from there, we will have our compiled program and any user-specified inputs. Those could be both public and private. Those are fed into the VM, and it'll generate a trace record from there. So that trace record is a complete record of that computation that's executed from running the program. And that trace record would then be fed into the zkVM, and that contains the prover. We'll look into some more specific components of the prover, but then as a result, it will generate that final output proof. So that's just like the big picture, like overview of how zkVMs work. Now we'll take a bit of a deeper look into zkMIPS specifically. This is a broad step-by-step overview on all of the components that are within zkMIPS. So this process can be separated into 3 different parts here. We have our first part relating to program execution, and then after that step is completed, we have proof generation and then the proof verification phase. So in our first part of the program execution, we take a program and it's written in a higher level language. In our case, we are compatible with Go and Rust right now. So that program is fed into the MIPS compiler, and it'll compile that program into an ELF binary. And that's just the executable format for MIPS. That file will be readable to the VM once we convert that source code into machine code. So that's why we complete that step. But from there, we'll have the ELF loader, which basically loads that binary into the MIPS VM. Then the MIPS VM will execute that compiled program, and it'll generate that execution trace or the trace record. So the prover can use the execution trace to prove the program. And I just want to mention that any high-level language can be compiled to MIPS. We'll get a sequence of MIPS instructions as a result. So how this looks like is that after each instruction is executed, which we show over here, we'll get a value for each register that's based on the instruction. So as you can see, for example, in this first row I here, it's basically saying like add the value from register 5 to the value in register 6, put that in register 7, and we can see in the corresponding trace table that it is true. Well, 13 plus 21 is 34 over here in the corresponding row. After going through all of these instructions, we'll get this entire trace table. So this entire table over here. And remember that the trace table is a representation of that execution trace that was generated from the VM. So then the prover will take that generated execution trace. It will check that the program was correctly executed and then generate a proof for that. And there are 4 main proof layers that are involved in zkMIPS specifically, or the 4 main proof systems. So we're using Stark, Logup, which is a subset within Stark, Plonk, and then also Graph16. So just as a overview of how these proof systems are used within our zkVM. First, the execution trace, which is shown over here. It's split into individual segments. Segments are just small sequential executions from the program. With these segments, they're then divided into modules. Those are even smaller executions from the segments. So by splitting the program into segments and then getting them into modules, it really helps with that succinctness aspect and just lowering the overall computational expenses that come with it. So over here, the instructions of each segment, they're divided or they're placed into groups of the 4 module tables. So over here, we have arithmetic, control, logic, memory, depending on the operation that's being performed in each instruction. So if the operation is arithmetic, the instruction will go in the arithmetic table. If it's a logic-based operation, it'll go into the logic table, and so on and so forth. So now we reach the first layer of this proving stack, which is involved using Starks. Those modules that we just had in the previous step, they will be proven independently with a protocol called Fry using Stark proofs. And as a result, we'll have these arithmetic, memory, logic, and control proofs that are all generated. And in the next step, we'll use a lookup scheme called logup, and it shows that a segment is contained in the modular table and is used to prove that the program instructions were correctly verified in their specific modules. So all of those modular proofs, which include like what we saw, the arithmetic, the logic, control, memory, they're all combined into one single proof for each segment. Now in this next part, which uses the Planck system, all of the segment proofs from the previous layer will be recursively combined using continuation into a single proof. And that single proof will prove the correctness of the entire program trace. Now, this last part is optional for the proof generation process, but in our case, in order to enable some on-chain computation, this final continuation proof is turned into an EVM-friendly format using Route 16. So that allows that final proof to be verified back on the L1. And this final proof is the zkMIPS proof. It shows the correct execution of the entire program. I just want to mention that most of these techniques that we applied, like splitting into segments and then modules, and then using these different proof systems, the goal of that is just to decrease the overall final proof size and also minimize the amount of proving time. So the final part of that process, which is external to the proof generation, is the proof verification. Once we have that final proof that's been generated, the verifier will verify the results of that executed program using the proof. So it can check the program and then it will accept or reject the result. So in our case, the verifier comes in the form of the smart contract. Now, as an overview of this process, it always starts with an end user's action, like what we saw in our proof's lifecycle. In our case, the end user wants to prove the correct execution of a program, and then we'll have that program be executed. So the program that the end user creates will be run in zkMIPS's execution environment. That program will compile to MIPS so that it's readable to the VM. And then a proof for that program's correct execution can be outsourced to ZKM's proving service, which is available for all of you to use if you apply to it, or you could just do it locally if you have the hardware requirements to do so. And then from there, once the zkMIPS proof is generated, a verifier contract will be used to verify the proof. And in the case of proving the correctness of blockchain-based transactions, once that proof is verified on-chain, that transaction is considered to be done and settled. And applying this more specifically for zkMIPS, we have the same steps, but the only difference is that the programs will be specifically written in Rust or in Go as now, and then the program will compile into zkMIPS's execution environment and will be compiled to specifically MIPS. And then the rest of the process, which includes the generation, verification, and settlement, remains the same. And looking at how this works in an example, ZKM is building an entangled rollup network, so L2s can be used as interoperability mechanisms for facilitating these cross-chain actions. And you can do this without having to implement an actual bridge. So you don't need to consider the architecture there, and there's some security risks that are also involved in using a bridge. So we don't have to worry about those concerns anymore. But in this case, say we want to transfer 100 USDT between two different networks. In this visual right here, we're transferring 100 USDT from Ethereum to Avalanche using this universal L2 system. So first, that 100 USDT, it's deposited into the Ethereum L2. Then a proof that that 100 USDT was burned on that L2 will be generated off-chain. That proof will be verified by a verification contract on the destination chain. In this case, our destination chain is Avalanche. And then once we have that proof that's verified, that 100 USDT can be minted and then withdrawn to the Avalanche L1. So that user will receive that 100 USDT on the Avalanche layer 1. So this makes it so that we don't have to implement an actual bridge when we're trying to make some cross-chain transfers, in this case, between Ethereum and Avalanche. And I just want to mention that this diagram was taken from ZKM's settlement network page, so you can go visit that and explore some other use cases if you're interested. Now, going into the demo portion of this, we are going to write a Rust program that proves that a user knows the value of a corresponding SHA-256 hash. So we'll generate a proof locally for this example. If that proof is valid, we'll deploy a verifier contract, and then we'll post the proof on a verifier contract to verify it. If that proof is valid, we'll be able to mint an ERC20 successfully. And actually, I'm just checking time right now because we are running a bit out of time. Instead of generating it locally, we're going to use the proving service to do it. So the benefit of the proving service is that you can quickly generate proofs using the computational resources that ZKM has. You don't need to do it on your own end. So we'll be doing that instead. I'll be showing you that in the demo because of the time that we have. But if you are interested in learning how to generate it locally, I'll link some resources as well for you to try that out. So over here, our first step is writing the actual programs that we want to prove the execution of. For our zkVM, we have both a guest program and a host program. So the guest program will execute the ELF binary that's proven inside the zkVM. So this includes reading the inputs provided by the host. It includes writing those private outputs to the host, and then committing any public outputs to the journal. And then from here, we have also the host program. So we have to write two different types of programs, but this host program will set up the environment for the guest program and evaluate the results from the guest execution. So what the host will do, it'll supply the inputs to the guest program. It'll evaluate those private outputs that the guest previously sent to it, and then it'll also evaluate the public journal output that's provided by that guest. So taking a look at the guest and host programs for this example on proving that a user knows the value of a corresponding SHA-256 hash, we can see here that these lines are getting the user inputs. And then this next section here, we will evaluate the result of the computation that our program is performing before we commit those public outputs and the actual result for the proof. And this host program, on this right side, we're basically just over here splitting the ELF program into segments, loading the inputs, and also the public journal outputs from the guest. So that's just an example of what a program looks like if you want to generate the execution of, and specifically for proving the value of a SHA-256 hash. Now, for generating your proofs, there's a couple of ways that you could prove your guest program. As we previously talked about, you could do it locally or using ZKM's proving service. So if you are interested in trying out the proving service, I linked here the application page. So you just need to put in some information, and then you can be added onto the whitelist so that you can use the service. In terms of the general steps, we'll compile that program into the MIPS ELF, split that ELF into individual segments, and then prove and aggregate those individual segments together. And then after you aggregate the proof, you should get a verifier folder with these three JSON files. So it includes the common circuit data, proof with public inputs, and this file over here, the verifier only circuit data. We'll use these files for the proof verification part. So over here for this first part of the demo, I have a pre-recording that I will make into 2x speed just to save time. So this proof generation part does take some time. We unfortunately are not able to do it live, but once you pull the latest version of the repositories, which I will link in the next couple of slides, you should go to the ZKM repository, and I'll be using here the Golang version of the SHA-256 program. And the functions of that program are essentially the same. It's just written in Golang instead of Rust. You can try either one, or you can try both and see. But it's essentially just performing the same actions. So over here, our first statement, we will set our default variables. Hopefully you guys can see it. I'm going to check if we can zoom in. Okay, it looks like we can't, but over here in this first step, what we're doing is we're setting our default variables. So that includes our segment size, the arguments, and that will consist of the public and private inputs. And in this case, our public input is the hash. The private input is the value that the hash corresponds to. So in this next statement, we're compiling the Go program into the MIPS executable, and we'll produce the ELF file for the VM to read. And we're also going to export the ELF path. So that's what we're doing in this section over here. And then as our next step, we will, from here, compile the Go program into the MIPS executable. We're producing the ELF file for the VM to read. We're splitting the ELF into segments. And then as a kind of like a last step of this proof generation, we will be proving and aggregating those individual segments. So this step, after you complete all of those commands over here, it will take some time. So depending on the hardware that you are using, on my end, it took around 7 minutes. So we'll fast forward a bit. This is just the process for the proof being generated. But after it's done, and it just completed over here, you'll receive a verifier folder with those 3 JSON files that will be used to verify that proof. And I will mention that I'll send you guys these slides, so if you want to look over this demo video on your own, feel free to do so. But as you can see here, we have our 3 JSON files that we automatically generated from this proof verification. So now that we have our proof generated, the next step is the proof verification. So that includes creating the verifier contract. And so generating that verifier contract customized to the MIPS binary of the program. And we're using the verifying key that was created from the generation portion. And it will determine if the proof is valid or invalid. We'll also have a verifier.sol file. So that's written in Solidity, that's generated using the caller Go. And in verifying the proof, we'll post the proof to the deployed verifier contract. And this will compare the hash of the inputs to the hash of the outputs. So, I also want to mention that once that comparison is made, for a valid transaction, that proof is considered to be valid if the hash of that value that the user provided is the same as the hash of the output of the proof. So then in our case, in our example, once we have a valid proof, we can perform some on-chain action using that valid proof. In our case, we're going to be minting an ERC20 using the valid proof. So to start the on-chain verification process, change your directory to the verifier, and you should enter into it. So from here, we can build, I'll just fast forward a little bit. Since this second part of the demo also encompasses the proof generation, if you are looking at this on your own end, you should start at this spot after the proof is generated. Let me check really quickly the exact timestamp. So it should be right around here. Yes, so if you're looking at this on your end, fast forward the video to 256. The first part is an example of doing the proof generation using the proving service. But since we already have our proof generated, we only need to look at the verification part. So it starts at 256. And here we're entering into our verifier. And then in our next step, we are taking the proof that was generated and placing it into a separate folder. And then from here, what we can do is, I'll just fast forward this a bit. We can build and compile our benchmark program, and that's going to convert our proof into a Groth16 proof. Remember, in turning this into a Groth16 proof, this will enable our proof to be verified on-chain, and the step is required if you want to deploy your proof on a verifier contract. So you have to complete this step. And it does take some time, so that part might be a little bit annoying. On my end, it took around 10 minutes to do the conversion, but it is necessary if you want to verify it on using the smart contract. But over here, it's just doing that conversion process. So we'll fast forward a little bit. And over here, after it's done compiling, from here we can then have, as a result, after compiling that benchmark program, the contents in that file that you have with your proofs will be updated. And then from here, we can now build the caller file and use that to generate the on-chain verification contract. So we're using hard hat ignition over here. We will now run a hard hat test. And before doing that, we started running a hard hat node, and that will start a JSON RPC server onto the hard hat network so that you can do the ignition deployment in the next step. We'll run test. So over here, we're testing if a proof was submitted to be verified. If so, then it should pass. If not, that means that something went wrong and your proof wasn't successfully submitted, so you should redo that step. But now that we have that, we're able to deploy the verifier contract on the test network. We're using Sepolia, and as a result, you can see the deployed address over here, like where we deployed our smart contract. So then now you can call the contract using your deployed address, and you'll get the hash for the verified proof, which we have outputted over here. And you can take that hash and review all the transaction details for that hash on Etherscan. So we use the Sepolia network. So you go to Sepolia to view the transaction details. And it should say success as a result. So now that we've successfully generated and verified a proof, let's use the verifier to complete some on-chain actions. In this part, we'll be using the valid proof that was generated and verified to mint in ERC20. So going into this third part over here, now that we have done the successful verification, now we can change our directory to the use cases repository. And again, I'll link all of the resources to these repositories so you can replicate this on your end. And I'll show you that in a few slides. But over here, as our next step, we're going into our hard hat folder, and then we can redeploy the contracts. Before completing that step, I do want to mention under hard hat, there's another folder called test. So be sure to replace that Stark proof that you generated with the valid Groth16 proof after running the benchmark program. Be sure to replace that proof there with your newly generated program. So then we have as a result, if we skip forward a little bit, we have our deployed address, and we can replace that new contract address that we just generated in our caller file. So that's what we're doing right here. This is our old contract address, and we're replacing it with our newly generated one. And then from here, you can just go to your wallet, and then you can go and import that token contract address that you just generated. And right now, just going back really quickly, because we did not mint any new tokens, it should say 0 as a result. But going back, we can now build and compile that caller file and mint the ERC20, specify the address that you're using, And then what's outputted is a transaction hash that you can verify and view the details on Sepolia. So fast forwarding a little bit over here, it should say success as a result. If for some reason you used an invalid proof, it will say that the proof is invalid or that the execution reverted. Now going back, we can see that we have one ERC20 that's now minted on this contract because we were able to submit our verified proof. So that concludes our main demo to generate a proof for a Go program, deploy the verifier contract to verify the proof, and then using that valid proof to mint an ERC20. Here are just some resources that you can use if you want to replicate this process on your end. So we have our prover repository, our verifier repository, our use cases repository. In addition, for the on-chain action that we completed after we did the proof verification, it was minting an ERC20, but our DevRel lead recently created a new use case where you can mint an NFT using your valid proof. So you can go ahead and try that out if that interests you more than the ERC20 mint case. We also have some other examples over here. So we have a project template. It's like a boilerplate template that you can use for any new programs that you want to prove the execution of. We have a user guide and a quick start example as well. So these are all of the learning resources and also other types of requirements that you need in order to complete this. And I also want to mention that the DevRel team also developed a playground. It's a very easy way. Just go to playground.zkm.io to input a program, generate a proof, and verify it without having to do any sort of installation or setup on your end. So it's a very convenient way to learn how you can generate and verify proofs. So just head over to playground.zkm.io if you want to try it out. Now for the actual workshop task, your main task is to design a use case for ZKM and submit it under a forum post in our F3 use cases channel. And I have the invite link for the Discord here. And then you can also complete the quiz and earn points from there. I linked the quiz over here. This first one on generating a proof using the playground, sometimes this does get a bit glitchy on some of our users' end, so I'm not making it required that you do that. But if you would like, you can try that on your own as well. Just the main couple of tasks that we're looking for is the use case submission and also completing the quiz. And here's just some more information on our socials. But yeah, that concludes our workshop for today. If you have any questions, let me know. And thank you all so much for joining.
Alex, thank you. Thank you so much for your wonderful presentation. And does anyone have any questions? Please raise your hand.
Yep, and then if you guys also want, I have my Telegram linked here, and then I'm also in the Build Her chat as well. So you can contact me if you have any difficulties during this process. I know in the last session, some people had some difficulty with accessing the ZKM points. I provided a guide in the chat that you can follow. If you have any further issues, feel free to reach out to me. And I just also linked the presentation in the chat. So if you want to take a look at any of the slides or the demo videos, feel free to do so.
Yeah, thank you. And also, we will have an official hour session in our Telegram and after the workshop. And here is our the link of our Telegram, and feel free to join us. And please feel free to ask any questions on our Telegram. Alice will be there and very happy to answer any of them. Yeah. And once again, I think thank you, Alice, for your presentation and to everyone who attended this workshop. Yeah.
Thank you so much, everyone.
Yeah, I think there's no question. So that's all for our workshop. Thank you. Thank you, guys.
Yeah, thank you so much, everyone. And I just want to say, oh yes, John, do you have a question? You can also type it in the chat as well. But I just want to mention, really quickly, I also left my email here, so I have both the Telegram and the email as well. So whichever way you want to contact me if you have any questions, let me know. But otherwise, thank you so much for joining. And again, really appreciate you guys for being here. All right, have a great rest of your afternoon or evening or morning, depending on your time zone. But have a great weekend.